Hey, you! Yes, you! You from the Telegram channel. You have asked for it. Many of you have sent me solutions for this challenge. And honestly, I'm thrilled because that one is really tricky and no one got it right. But many of you got very close. So I got myself someone who is very good at C++, who has a lot of experience. And he's going to explain to you how this challenge works. The challenge is to swap two variables without using a third variable. I really want to thank Mario Sieg from Kerbo Games, who has recorded this video. As said, I currently am not as experienced in C++ as I used to be. So he really came like a God-sent gift to me, because I right now would not be able to make such a detailed video. He really is explaining the basics but then goes in depth. Oh well, just watch it for yourself. And remember, share the videos with your friends and subscribe to this channel. I really need you. Alright, have fun watching.
Hello everyone, my name is Mario and today I'm going to take a look at the swap challenge. The challenge basically was to swap two numbers A and B without creating a third one. So as you can see, I have my two variables here and they have the values 10 and -6. And after the swap I want A to be -6 and B to be 10. So here we are just printing these numbers and let's give it a try. And as you can see, it's totally correct. A is 10 and B is -6. So yeah, the easiest way probably would be to just create a temporary variable to say like order T is equals to A is equals to B, and B is equals to T. So let's try this. And as you can see, A now is -6 and B is 10. So it swapped these variables, but this was not allowed because it would be too easy. Of course, in real life code you would just write std swap or use a third variable, as long as you're not copying a huge chunk of memory. So yeah, there were many approaches to this problem. Someone came up with this idea over here. Basically to just use arithmetic operators, add and sub, to calculate the differences between these numbers to swap them. So fine, let's take a look if it works. And does it work? Yes, it worked. A is -6 and B is 10. So sadly there is a huge problem with this algorithm. Basically you have to think about overflow. If one of these numbers is too big, then A is going to overflow. And this can cause some huge problems. For example, in C and C++, signed integer overflow is still undefined behavior. Unsigned integer overflow otherwise is okay, but it would still give you an overflow. And in C++ 10.20 we are going to get full complement wrapping. But if an implementation does not use complement wrapping, this could also lead to very weird bugs. So this algorithm does work for some numbers, but if the numbers get too big, then there is going to be an overflow and probably undefined behavior and wrong numbers. And trust me, bugs like this are almost impossible to catch. So this is a nice approach. There is also another approach like this, but it uses multiplication and division, but it's exactly the same. It's exactly the same algorithm, basically, just with multiplication and division. But the problem with that is that there can overflow can happen there too. Also, multiplication and division is even slower than addition and subtraction. So yeah, there is a best way to do it, and that is the XOR way. We're going to use the Bitwise XOR instructions. Bits are basically the lowest unit of memory, and they can either be 1 or 0. And we have bitwise operations which are just operating on these bits. So for example, we have the bitwise AND, the bitwise OR, the bitwise XOR, and the bitwise complement. So we are going to use the XOR operation. If you don't know how these work, just search in the internet. They are basically just comparing the bits to each other and then setting them according to their values. This, for example, the bit complement operator is just converting all zeros to ones and all ones to zero. So we're going to use XOR. So we're going to say A XOR equals B, B XOR equals A, and again A XOR equals B. Let's give it a try. And as we can see, it swapped the values correctly. A is -6 and B is 10. Without undefined behavior, without overflow, completely 100% correct. Because we were just fiddling some bits around, we were just switching some bits on and off, and yeah, basically we couldn't overflow anything with that. Also, XOR is one of the fastest operation available on the CPU and in the x64 and x68 assembler instruction set. So it's really fast, and yeah, many algorithms are actually using this under the hood. So there is another really nasty thing we can do. We can use these swap algorithms also with floats. So I'd say yeah, let's do that. It's very nasty, but I'd say it's for learning purposes. So first of all, what we have to get the bit representation of a float. So we're first going to convert A and B to float, and we're going to say like some random float numbers, and imagine that we have to somehow apply bit operations to floats because they're restricted to integers. We cannot do A, for example, OR equals B. It's going to get an error. Cannot apply binary OR to float and float because the float does not have any operators for these bitwise instructions. So we have to do a little ugly hack. So we are going to convert the float to his bit representation. Sorry. A float is 32 bits wide. So we are going to choose a 32-bit integer. We're not going to say int or unsigned because remember these types are exotic. They can have different sizes on different systems. So we're going to use the fixed size integers and going to say, for example, a int, which is the corresponding integer of a basically, equals dereference reinterpret cast uint32 pointer ampersand as a address of and a. So what the hell is this? So this ampersand here is the address of operator, also known as load effective address. In assembler a little bit, it's basically the same. So it's returning the pointer of a. And this pointer is a pointer to float, so it's of the type float. And reinterpret cast basically says to the compiler to just treat this pointer as another type. So this does not compile to any assembler instruction. It just say to the compiler, hey, this is now an unsigned 32-bit integer. And of course it is completely unsafe. You could cast a string pointer to a boolean pointer using reinterpret cast, and you're going to get the biggest garbage values ever. So be really careful with that, and only use it if you're really knowing what you're doing. Also, if you're going to store these pointers, you're probably going to get undefined behavior due to the aliasing rule. But it is another story. So here we're immediately dereferencing the pointers, so just creating a copy. We're not aliasing any pointers. And this is basically the bit representation of A. And let's just print this instead of A. Like this, and this is... yeah, here we go. So let's give this a run. And as you can see, yeah, this number over here, the bit representation, has nothing to do with the number A had before, because floating point numbers have their own standards and representations. So this is the bit representation basically. And we can apply XOR operators to them. So basically, if we are going to be ugly, we can say A XOR equals, and then here we're going to choose B, And let's copy and paste this because it's exactly the same as the end. And here we're going to say B, and here we're going to say A. And let's print A again, and let's print B. And yeah, let's just take a look if it works. And as you can see, it worked. A is now this number, oops, and B is now 3.14. So yeah, this really works with pointers. But actually, this is fairly okay, but it is not the perfect solution, because we could make it even more nasty. We could really apply this operation to pointers themselves. What I want to say is, what if we have a float pointer called P1, which points to A. Oops, I'm sorry, I got a new keyboard and I'm still not really familiar with it. And this one points to B. And let's call them PA and PB to be clear. So what we can do, we could basically just convert PA basically to U in PTR and then apply the XOR operations to them. So let's do that a little quick to show it. So let's replace all these appearances over here. And yeah, there's another problem. We are not going to convert it to U in 32 because a pointer is 32 bits in size on a 32-bit system, but 64 bits in size on a 64-bit system. And if we are on a 64-bit system, so a pointer is not going to fit into this number. So we have to use the STD U and PTRT, which is exactly the perfect type to store pointers as integers. It has the exactly size to store the pointer depending on what kind of system you are. So here we go, let's give it a run again. And as you can see, it swapped it again. Now A is again 6.666 and B is again 3.14. And this is basically the other approach to convert pointers to any other type and then applying the bit operations on the integer representing the memory address themselves. Of course, please never ever do this in real code. This was just for learning and purposing. You're going to get undefined behavior really fast and nasty bugs, but you could use this to, for example, show someone as a trick or maybe just to play around with. I hope that you like this little introduction to bitwise programming, low-level programming, and also pointers and stuff. Yeah, and I wish you a very beautiful day, and I hope to see you soon. Bye.